This is Grand Admiral Rosine, following the physics directive to explain conceptual modern physics. In this video, I will be explaining Galilean relativity. Now, Galilean relativity is a classical principle, not modern, but it is necessary for understanding Einstein's relativity, which is modern. At the end, I will explain the problems with Galilean relativity to lead into the modern piece. To imagine Galilean relativity, imagine a car driving towards a stop sign. You would say that the car is in motion and the stop sign is at rest. But now imagine that you are sitting inside the car. From your perspective, it looks like the stop sign is moving towards you and that you are at rest. According to relativity, both perspectives are equally valid. This is because if motion is absolute, then one could argue that neither the car nor the stop sign are at rest since the Earth revolves around the sun. But the stop sign definitely seems to be at rest to a person standing on the street, and the car does to a person inside of it. To explain this, we must visualize motion in reference frames. Since the sun, stop sign, and car all disagree on which objects are in motion, it can be concluded that motion is relative to the observer rather than being absolute. Therefore, we can say that the stop sign is at rest in a reference frame moving with the surface of the Earth, while it is in motion in a reference frame moving with the car. To simplify the situation, say that the car was moving towards the stop sign at a constant speed. The car would view the stop sign as moving at the same speed, but the opposite direction. According to Galilean relativity, if we knew the speed of the car relative to the stop sign and someone was running away from the car, we would subtract the velocity of the car from the velocity of the person relative to the ground to find the velocity of the person relative to the car. If the person was towards the car, we would add them. Galilean relativity can also be visualized on a spacetime graph, with the x-axis representing space and the y-axis representing time. On this graph, you can draw the path an object takes through spacetime. This is called its world line. A vertical world line is of an object at rest, while a tilted one is in motion, since as its position in time changes as its position in space changes. To represent the rest frame of the moving object, which is a reference frame in which that object is at rest, we should tilt the y-axis so that from the new reference frame, that object stays in the same position in space as time passes. The problem with Galilean relativity is that, according to many tests and observations, the speed of light remains constant in all reference frames. This means that if someone chased a particle of light, that light would still move at the same speed relative to them as someone standing and watching. This can't be modeled by Galilean relativity, since if we draw the world line of light and tilt the y-axis, its speed should change. In the next video, we will discuss the solution to this problem as we start special relativity. If you enjoyed this video, please give it a like. If you want to further explore conceptual modern physics, please subscribe to my channel and join me in the Physics Directive. Long live the Empire.